तो
तेका न्हू तेजो न्हू लॅपटॉपाचो जो आसा न्हू सिग्नल
हे म्हणून
मातसो कॉल कर कर्टन तू सांग
Dr. Meeta Amonkar, wishing a wonderful evening to one and all. Ladies and gentlemen, it is a proud moment for us at Ponda Education Society's Ravi Naik College of Arts and Science, Farmagudi, Goa, to host a public lecture on Indian lunar missions, which is a part of the 22nd National Space Symposium, jointly organized by Indian Space Research Organization, Goa University, Government of Goa, and other organizations. It gives me an immense pleasure to welcome Secretary, Ponda Education Society, Dynamic Youth Leader and Chairperson, Ponda Municipal Council, Honorable Shri Ritesh Naik, to grace this occasion. A warm welcome to you, sir. On behalf of Ponda Education Society's Ravi Naik College of Arts and Science, the management, Principal, Professor Vikas Pisulekar, Vice Principal, Dr. Satish Keruskar, staff, and students, we extend a heartfelt welcome to our esteemed guest speaker, Shri A.S. Kirankumar ji, Chairman of the Apex Science Board and former Chairman of ISRO. His contributions to the Indian Space Research Organization have been exemplary and have significantly propelled India's advancement in space exploration. We are truly honored to have you with us today. A very warm welcome to all the special invitees, privileged management members, distinguished guests, organizing committee members, faculty members and administrative staff of various educational institutions, student enthusiasts, and media persons who have gathered here for today's program. Due to prior commitments, Honorable Minister for Agriculture, Government of Goa, and President, Ponda Education Society, Shri Ravi Naik sir, could not make it for today's program. Greetings to the guest speaker and best wishes are conveyed to the entire team. Before we proceed with the program, I request Mr. Vishnu Naik, a maestro in the realm of music, to bless us with an invocation song.
Omkar Swarupa, Omkar Swarupa, Omkar Swarupa, Tuja namo, Tuja namo, Omkar Swarupa, Sadguru Samartha, अनाथांच्या नाथा तुझं नमो, तुझं नमो, तुझं नमो, तुझं नमो, तुझं नमो. नमो माय बापा गुरु कृपा घना, तोडिया बंदना माया मोहा, मोहजाल माझे कोण निरशील, तुझ वीण दयाळा सद्गुरु राया. तुझ नमो, तुझ नमो, तुझ नमो. सद्गुरु राया माझा आनंद सागर, त्रैलोक्या आधार गुरुराव, त्रैलोक्याधार गुरुराव, त्रैलोक्याधार गुरुराव. गुरुराव स्वामी असे स्वयं प्रकाश, त्या पुढे उदास चंद्र रवी, त्या पुढे उदास चंद्र रवी, त्या पुढे उदास चंद्र रवी. रवी शशी अग्नी मेघ तिच्या रूपारवी, शशी अग्नी स्वप्रकाश रूपा नेणे वेद, स्वप्रकाश रूपा नेणे वेद. तुझ नमो ओंकार स्वरूपा, सद्गुरु समर्था, अनाथांच्या नाथा तुझ नमो, 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 तुझ नमो.
We owe our gratitude to Vishnu Ji for gracing us with a divine musical offering. I now request respected Principal Professor Vikas Pisulekar and Vice Principal Dr. Satish Keruskar, Ponda Education Society, to escort the dignitaries to the dais. Kindly be seated. Thank you. Today, we have the privilege of delving into one of the most remarkable achievements in space exploration, the Indian Lunar mission. This mission stands as a shining testament to India's prowess in the field of space science and technology. As we embark on this momentous occasion today, may I now invite our principal, Professor Vikas Pisulekar, to formally welcome the gathering.
Namaskar, and a very good evening to you all when we have assembled here to listen to one of the distinguished space scientists of India. As you are aware, Goa University, in collaboration with ISRO and other organizations, has organized biannual 22nd National Space Science Symposium from 26 February to 1st March 2024. As a part of this symposium, 3 public lectures at Sankelim, Margaon, and Ponda are being organized. And today, this evening, the 3rd lecture is being organized by our college, Ponda Education Society's Ravi S. Naik College. On this occasion, we have got with us Padma Shri A.S. Kirankumar ji, the chairman of the Apex Science Board and former chairman of ISRO. He is a highly distinguished space scientist and engineer with over 4 decades of service in ISRO and being the chairman between 2015 to 2018 of this great organization. He has immense contribution to the design and development of electro-optical imaging sensors for airborne low Earth orbit and geostationary satellite from Bhaskara TV payload to the Mars orbiter, or better known as Mangalyaan mission payloads. Shri Kirankumar ji was the principal investigator of Chandrayaan-1, the first Indian deep space mission which was launched to orbit the moon and to dispatch an impactor on the moon's surface in 2018. The most important discovery of this mission of 2008 of the Chandrayaan-1 was the discovery of presence of water on the moon. And as you are aware, leading to this Chandrayaan-1, we have now Chandrayaan-2 and Chandrayaan-3, on which successfully on 23rd August 2023, we could have our lander, Vikram lander, and Pragyan rover, which could take a 14 days ride on the moon or 1 moon day ride during this particular mission. And India is perhaps the first country to land its lander on the south pole of the moon. So therefore, it's a great achievement that we have got this scientist among us, and I expect all the audience here to give her a great round of applause. Because these are the personalities which makes the ISRO, the India, the space science in India and in the world one of the most immense popular and one of the most, as far as my young students from different schools, higher secondary and colleges are concerned, to look at space science as one of your career option as the years go ahead. We have also got among us the young dynamic Shri Ritesh Naik, the chairperson of Ponda Municipal Council and secretary of Ponda Education Society. I welcome you, sir. My vice principal, Dr. Satish Karuskar, management members of particularly GVMs, Shri Bhaskar Khandeparkar, the chairman of general body, and Shri Krishna Shetty, the chairman of working committee, and his other members from the management committee. My own Ponda Education Society's treasurer, Shri Prakash Balveji, all my other colleagues, principal from the sister institutions of Pharmacy College, B.Ed College, the high secondary school, all other principals attending from other colleges, high secondaries and schools, my colleagues of the college, other faculties, dear student, and press, media, and friends. We have shown the world what we can do, because if you remember, the Mangalyaan which was launched was for just $74 million, whereas at that time, the movie which had come also had spent about 100 million rupees. So we can see we have got persons like Padma Shri Kirankumar ji doing a wonderful job as far as space is concerned by using very less amount of expenditure. And this is one of the greatness, that indigenous technology that India has developed today has made ISRO one of the best in the world, and many European countries or European companies who want to launch their commercial satellites are now looking at ISRO rather than other launching organizations like NASA, European Union, etc. So therefore, when we see these personalities here, if some of you, the young people, idolize them, imbibe, inculcate the discipline in which they have brought this laurel to us, I think by 2047, India will definitely become Viksit Bharat. We will not only be doing well in other fields of life, but we will also do very well as far as space science is concerned. Just other day, you might have seen the 4 astronauts who are going to go in our Gaganyaan mission, which will be there in 2025, where unveiled to the world by our Prime Minister. And also by 2047, it is expected that India will have its own space station, space laboratory in the space, doing lot of research which is required. Because world is growing, we are growing in terms of population, and we will need lot of research coming from the space agencies like ISRO, with the other CSIR and other labs. And therefore, all my young students who are coming from the schools, higher secondaries and colleges, this is the opportunity for you. The growing India, Viksit India will definitely give lot more to offer to you. And if you can accept that, I don't think the 21st century, which we say is now going to belong to India, I think that dream will definitely going to come true. Once again, I welcome you, all of you, for this particular public lecture. And I'm personally thankful to Shri Kirankumar ji, as well as to the Goa University and my management, Shri Ravi Naik sir, who could not be here because of his pressing engagement elsewhere. However, our secretary Ritesh Naik is here because we are organizing this particular function with the best motivation, best help, best assistance coming from them, as well as from other government agencies. And I hope the lecture which Shri Kirankumar ji is going to deliver to us will be really enlightening, because 3 successful Chandrayans makes us to look at the moon for not only for future landings, but to make the moon as a satellite where we can have human habitation in near future. Thank you very much for listening to me.
Thank you, sir, for a graceful and insightful welcome address. A warm welcome is incomplete without a gesture of appreciation. Extending a floral welcome as a token of our gratitude, love, and respect to our esteemed guest. I call upon Mandakini ma'am to present a bouquet of flowers to esteemed speaker for today's program, Shri A.S. Kirankumar ji, as a kind gesture of love and gratitude. Dr. Preetham, presenting a bouquet of flowers to Honorable Secretary, Ponda Education Society, Shri Ritesh Naik. Your presence here adds immense value to our event. Now, Ms. Sasha will present a bouquet of flowers to our respected principal, Professor Vijay Pisulekar, and Ms. Sriveni to present a bouquet of flowers to our Vice Principal, Dr. Satish Keruskar. Thank you. Now, it's my privilege to invite Honorable Secretary, Ponda Education Society, Shri Ritesh Naik sir, to kindly address this esteemed gathering.
Good evening. On the occasion of National Symposium organized by Government of Goa, Goa University, and also by Indian Space Research Organization, we have on stage eminent scientist, Professor Shri A.S. Kirankumar ji, Chairman Apex Science Board and former Chairman ISRO, Professor Vikas Pisulekar sir, Principal of PS College of Arts and Science, and also Dr. Satish Keruskar sir, Vice Principal. And also we have with us the Management Committee. There's Mr. Bhaskar Khandeparkar from Vidya Prasarak Mandal, Mr. Shetty from Vidya, Chairman of Governing Council, and also all the committee members of Governing Council of GVM's board, and also we have our treasurer from Ponda University, Mr. Prakash Bave, all the teachers, non-teaching staff of Arts and Science College, and also we have with us principal of Pharmacy College, and all the students who have come from various colleges, higher secondary school. I think we are very much privileged, and I think this is a great moment for us. We have with us ISRO, former ISRO chairperson, Shri A.S. Kirankumar ji. I think all of you are waiting for this opportunity to hear from him, and there will be Q&A and question answers session. I think you will participate and will take, and this is the lecture which is being held to bridge a gap between the space and the society. I think as you all know that India's journey into space has been incredible. It began in the year 1961 with ISRO, when the ISRO was formed, and since then ISRO has been using space technology to help people to do research. And as you know, our first satellite, Aryabhat, was launched in 1975. From there, we have made many satellites for different purposes. And one of our biggest achievements was in 2013, when we sent the Mars orbiter mission to Mars, and in 2019, Chandrayaan was sent to explore the moon. So India has successfully launched 3 Chandra missions and successfully landed Vikram lander on the south pole of the moon. It fills me my heart with pride to say that India is the only country in history to do so. And our space organization is exploration isn't just about exploring space. It is about using science and technology to make a positive impact on people's lives. It helps in farming, dealing with disasters, providing health care, and predicting the weather, among many other things. And now we are gearing up for an even bigger step. As you all know, sending Indian astronauts into space with the Gaganyaan mission and launching our space laboratory with our own astronauts before 2047. I think the lecture by Honorable Sri Vikram Sarji, Kirankumar Sarji, will be enlightening you all, and I think you should take this opportunity to explore when he explains to you all the lecture which will be delivered. So you should take all the things which he guides you and which he tells you about the space and all the recent technology where lot of things are happening in space, and to bridge the gap between society and space. So I think it's going to be a very fruitful session, and I wish you all the young minds who have come here my best wishes, and you will take something good from here, good knowledge, and which will be good, which will be put in good use for the future of the nation. Thank you.
Thank you, sir, for gracing us with valuable insights and also your kind motivation to the audience. I would like to invite Dr. Ranjita to come forward and introduce our eminent speaker for today's session, Shri A.S. Kirankumar ji, who will shed light on the achievements of Indian lunar missions.
Thank you, Dr. Meeta. A very good afternoon to one and all present over here. I feel honored to introduce to you all today's guest speaker, Shri A.S. Kirankumar sir, Chairman, Apex Science Board, former Chairman, Indian Space Research Organization, ISRO, Government of India. Sir Kirankumar ji has served as Secretary, Department of Space and Chairman, ISRO during 2015 to 2018. Sir holds Master's degree in Physics from Bangalore University and MTech degree in Physical Engineering from IISc Bangalore. Sir has steered implementation of applications-oriented Indian space program, which has facilitated rapid development of our country in many important spheres of Earth observation, communication, navigation, meteorology, and space science, as well as development of indigenous launch vehicles, and related technologies for providing assured access to space. Sir has led design and development of more than 50 electro-optical imaging sensors flown over various spaceborne platforms starting from Bhaskara in 1979. His role in success of Chandrayaan-1 and Mars Orbiter mission has been significant. Sir has been President of Aeronautical Society of India, Fellow of National Academy of Engineering, National Academy of Sciences India, Indian Society of Remote Sensing, Institution of Electronics and Telecommunication Engineers, Indian Meteorological Society, and many more. In his lengthy and a very fruitful career, Sir has made valuable contributions to coordination group of meteorological satellites, expert team on satellite systems, Indo-US Joint Working Group on Civil Space Cooperation. Sir has co-authored 85 publications in various national and international scientific journals, and also he has done presentations of his research findings during the national and international conferences and symposia. Notable honors conferred on him include Sir M. Visvesvaraya Senior Scientist State Award in 2013 by Government of Karnataka. In recognition of his contributions, he was conferred Padma Shri by Honorable President of India in 2014. Sir is recipient of Rajotsava Award, Sir Visvesvaraya Senior Scientist State Award in 2015, Lifetime Achievement Award by Andhra Pradesh Academy of Sciences in 2016, Bharat Ratna Sir M. Visvesvaraya Centenary Award by University of Mysore in 2016, H.K. Firodia Vijay Ratna Award in 2017, ISRO Lifetime Achievement Award in 2018. Sir has been bestowed upon International Von Karman Wings Award in 2018, instituted by Aerospace Historical Society together with Graduate Aerospace Laboratories at the California Institute of Technology. For his valuable contributions in the field of space science, Sir Kirankumar ji has been conferred highest civilian honor of France by Government of France in 2019. So we are very fortunate to have you with us over here today. With this brief introduction, may I now request Dr. Meeta to kindly take over. Thank you.
Thanks, Dr. Ranjita, for an elaborative introduction of today's guest speaker. It is my distinct honor to invite a visionary leader whose guidance has been instrumental in shaping India's space endeavors. Shri Kirankumar ji, the former chairman of Indian Space Research Organization, to address the gathering.
Good afternoon to all of you. It's indeed a great privilege and honor to be present here and share with you the developments that have happened in India in relation to Chandrayaan activities. And at the outset, let me thank the Ponda Education Institution for providing me this opportunity. And today, as you see, India is forging ahead in all directions. We have seen from getting our independence way back in 1947, we have moved. Today we are the 5th largest economy, and before 2047, century of our independence, we want to reach the topmost. And if that has to happen, who has to work for us? Do you think people from outside India will come and help us in doing this? Definitely not. It's you and me who have to work, put our sweat and blood, and make India reach the position we are aspiring for. In the past, if many Indians were planning to go outside India, it was because they found in those places a situation or an environment which is more conducive, and that happened because the people of that country, America or Europe or even Australia, those people had put their sweat and blood and created an environment where others could come and contribute to their growth. But then today you have seen how India is making a big difference. It's emerging strong in all areas. And also you have seen how India has dealt with very difficult situations, whether it is COVID or today in digital domain, digital stack, how India is actually making a significant difference. And in the recent past, you have also seen how India is making use of the space technology for providing very important solutions to the problem, which I'll touch upon during the course of my presentation. How ISRO started making use of a new technology of space, for finding solutions to many of the problems. So in this context, I would really appreciate the Ponda Education Society for bringing in all you youngsters and giving you an opportunity to listen to what has been happening in the area of space and the recent developments. And it's only when more and more exposure and more awareness is there that you will be able to contribute to what is expected from you. You are the people who are going to take India to its numero uno position by 2047. And for this, more and more efforts like what is happening today is necessary. So let me once again compliment the organizers of this program for doing this and also giving me an opportunity to talk to you about the space technology and its contribution to India's growth. Thank you.
Thank you, sir. Your expertise and leadership have been pivotal in elevating India's space program to new heights. It is indeed a golden opportunity for each one of us to enrich and enlighten ourselves on Indian lunar missions. Without further ado, let us commence this extraordinary journey into the mysteries of space and start the resourceful session on Indian lunar missions. A kind request to Shri Kirankumar ji to start with the session.
Yeah, good afternoon to all of you. So what I intend to do is initially just give you a glimpse of how India started its space activities before we get into the Chandrayaan mission itself. Probably you are all very familiar way back in 1957, humanity got a new way of, a new technological capability, a very disruptive technology. For the first time, an object was put into space by Russians in 1957. And at that time, India was a fledgling democracy, just 10 years into independence. After centuries of external rule, it was struggling to provide food, shelter, education to its citizens. And at that time, we had great visionary scientist, Dr. Vikram Sarabhai, who was looking at how this capability of going beyond planet Earth can help India make big strides and provide necessary solutions to the specific problems we were facing. And in that, what Dr. Sarabhai did was, in a way, convinced his friends across America, Russia, France, and Germany, telling them that in India we have a very unique place called a geomagnetic equator in Tumba, in Trivandrum. And if we conduct upper atmospheric research by sending these sounding rockets into space, it will benefit the scientific community. And with that in mind, he was able to get sounding rockets. In a way, you can say, today we are all familiar with do-it-yourself kits. So getting those sounding rockets in the form of kits, got it assembled and launched from Tumba. And this was done way back in 1963, the first of that. And you have seen, in fact, the rangoli that is done outside also has captured that the rocket being carried on the cycle. So that's how India started its program. And what made a difference is India is the only country which started working on space technology for non-military purposes. All other countries work for space technology or use of space technology from military purpose. What Dr. Sarabhai also did was, he convinced Americans that they should allow us to borrow one of their satellites which they were building in the mid-70s, and using that satellite, provide communication, broadcasting capability across the country. Today, we are all very familiar, a small set-top box with a quarter-meter antenna on our rooftop, we are able to see the television program. Way back in 75, if you probably ask your parents or grandparents, they will tell only 4 cities in India had the privilege of looking at broadcasting service. At that time, what India did, ISRO did, was developing this capability of what is called direct-to-community sets, borrowing a satellite from America, moving it over Indian longitude. And probably you are also familiar that different objects at different heights from Earth take periods which vary from 1.5 hours to, like for Moon takes 28 days to go around Earth. So there is a place at 36,000 kilometers distance from Earth where the satellite takes exactly 24 hours, which means relative velocity with respect to Earth's rotation becomes 0. So the satellite becomes a tower at the height of 36,000 kilometers, and this enables 1/3 of the globe to be suitable for line of sight communication. So what India did was, in 2,400 remote villages, ISRO demonstrated that you can use the satellite technology for quickly reaching information to the people in the country. And both communication and broadcasting, if you see, India is 3.25 million square kilometers in size. An alternative that was available at that point is, every kilometer you put a microwave tower and then you can do communication. So if you see, if you had to cover the entire country, you would have required 3.25 million such units, and both time and effort would have been enormous, though the satellite way was the quickest, and that's what was demonstrated by India at that time. And another thing that was done is, in terms of weather, super cyclones used to kill many thousands of people. Using space technology, you can make sure that not only you learn about the arrival of the cyclone in the coastal region, but also prepare yourself for dealing with the vagaries of the super cyclone. Today, with the satellite information, you can tell exactly which place the cyclone is going to come days in advance. So the disaster relief agencies are able to evacuate people there and save lives. In the earlier decades, it used to be tens of thousands of people used to lose their life. Today, with the satellite technology, we are able to make sure that such a loss of life does not happen. And another thing was enabling using satellite, both for telehealth and teleeducation. And another very interesting, of course, you can also collect a lot of data about regions and then see how changes are occurring, whether it is snow cover or other aspects, and study about climate. So that is possible. Then with this kind of thing, today you have a large number of satellites operating, collecting data, because you can visualize satellites do not have any state boundaries or national boundaries to worry about. From space, everything is accessible. You can collect data and make use of it for various applications. And India has built a significant amount of satellites and then providing various applications for this activity. And in doing this, not only probably one more aspect I missed, maybe I should tell you that before I go further. So one other thing that happened when Dr. Sarabhai was doing this experiment was he had to convince the fishermen in that region, telling them that you vacate this place for us to conduct these rocket experiments. One day the country will benefit. What has happened subsequently is from 1999 onwards, we have been able to provide specific information to the fishermen, telling them where they can go for fishing. How is this done? By looking at the color of the ocean from the satellite, identifying from that color where the chlorophyll is, and from that chlorophyll, identify where the fish food chain is, and through that, locate a place in the ocean where the fisherman is assured of catching the fish. Today, with our NAVIC satellites, we are also able to go one step further. One small battery-operated gadget is fitted into the boat of the fisherman, and this gadget picks up signal from the NAVIC satellites, not only locates itself where is in the ocean, and it communicates with the mobile in the hands of the fisherman. And in the mobile, there is an app which shows to the fisherman through a video compass mode where he has to go for fishing. Not only that, it tells him in his mother tongue any adverse situation because of heavy rains or wind speeds or even sea state roughness not being bearable. And many times you would have read in your papers that our neighboring countries capture these fishermen because they are wading into the waters of their national territories. And here, the gadget, the mobile, gives him alert in his mother tongue. So you can see in this example, this has been happening starting from 1999, and with our NAVIC satellites, today about 3 companies are making more than 1 lakh such units, and state governments are going to provide this to the fishermen. A person who does not know reading or writing is taking advantage for his livelihood of the most advanced technology of rocket, putting a satellite into orbit and its application. And then this act alone saves to the country between 15 to 20,000 crores a year, because the fisherman doesn't have to search for his fish catch. The amount of petrol and diesel he saves is what is saving in this fashion. So this is one of the very important development that happened, and what Dr. Sarabhai had actually promised the fishermen became a reality. Now, today with the kind of space technology capabilities, the various applications that are there, whether it is monitoring of the weather or even crop forecasting, crop assessment, and all this happens. And one of the things that happened is, the usage-wise, what happens is if you go to somebody and tell him what he is doing can be done very differently, the first reaction of that person would be, I know my job better, who are you to tell me? But then with lot of persistence, perseverance, you can make sure that you can bring in that technology for usage. The Honorable Prime Minister actually had made extensive use of this technology when he was the Chief Minister of Gujarat. And when he became the Prime Minister, we conducted an event in Delhi where all the secretaries of state and central governments were brought together, and they were showcased how space technology can be used for various usages, and since then, the usage has become extensively increased. And then what India did, in a way, you can see, it started addressing the use of technology for specific issues which it had, whether it is the solving the problems of the fishermen, education, health, or even with respect to monitoring, and also neighboring countries, you can see for surveillance and other various aspects. Today we have more than 60 plus satellites doing a lot of these activities. So in a way, when India started this program of space, it was looking at how it could address all these problems. And in this, one of the key things is what is called as a leapfrogging technology. That means, what is leapfrogging? See, you see, if you want to do a high jump, reach a certain height, you have to run a distance, generate enough momentum, and then using that momentum, you reach a height. But if you do not have even that much space for building up momentum, what do? You know, frogs, for example, they crouch at the same place and they can jump, and that is leapfrogging. And what India did was, whatever technology it was accessible to us, made use of it, but addressed it for solving the specific problems we had. And today, India is recognized globally for using space technology for many societal applications. While all this happened, world is not remaining stationary, it's moving ahead. So we also needed to do many other things. So that's what I'll touch upon now. That is the prime topic of today's talk is our lunar missions. So initially, when we started developing our capability, we were putting the satellites into low Earth orbit between 500 to 900 kilometers, where the satellite takes roughly 1.5 hours to go around the Earth. And using that, you can do communication, broadcasting, etc. And geostationary satellite, like I pointed out, is one which takes you to a height of 36,000 kilometers and appears to remain stationary with respect to you. Then, after we, in a way, built our own capability of going there, we were looking at moon, which was 385,000 kilometers when it is closest, and that is almost 10 times the distance from geostationary orbit. And then Mars is many million kilometers away. So these are the different capabilities that were required to be established. And then what was done is, all this when it is done, probably you would have read that we take a long time to reach moon or Mars or many of these. Today, why this is required is again what I was trying to tell you, leapfrogging. We had a lot of resource constraints and technological capability when you are building. Unless you have significant amount of resources, you cannot build a capability which is very strong. But then within what we had built, if you were to attempt and reach moon, we had to find alternate ways of doing it. So what was done is, when the rocket, what we have built, can put a satellite into a certain orbit, an elliptical orbit. How an elliptical orbit is reached is, this rocket takes the satellite to a particular distance from Earth, say 170, 200 kilometers, and from there, depending on how much energy you impart to the object, you get into an elliptical orbit where the point of release becomes the closest point to the Earth, and the other side, it becomes the apogee or the farthest point. If the launch vehicle itself cannot put the satellite directly to go to moon or Mars, what we did is, whatever elliptical orbit to which the satellite could be put by the rocket, we took that and built the capability in the satellite where every time the satellite comes to the perigee point, you add a small velocity to it. So because of that addition, you go to a further point. So in this fashion, you keep building up your apogee point, and then finally you can reach what is called as lunar transfer trajectory, or even Mars, or even Aditya when we have gone. In all these, we have made use of this capability, and using this method with the limited resource we had, we were able to perform actions which otherwise would have demanded launch vehicles of much higher capacity to be built. So here, initially you take every apogee point to be increased from the satellite orbiting Earth, and then after that you go to a point where it reaches moon, and at that place you do exactly reverse, because if you want to get into the orbit of any celestial body, what you need is, depending on at what distance you are there, if you give a critical velocity, it will go into a circular orbit. If you give less than the critical velocity, then you will get into an elliptical orbit, and if you put more, depending on what is your current velocity, things will change. So we had to do exactly reverse and then capture the moon. So if you see, in a way, what was being done is like this. Each time the satellite comes close to the perigee, you add some velocity, and the satellite keeps going further and further. So you can see the right-hand top side showing you what is the apogee point that is going 71,000 kilometers, and the next time it will go even. And we made use of all these opportunities to keep doing, so that it is like you have only a moped and you want to reach a faraway distance. So you do not have enough strong engines. So that is the way we built this system. And this was also in a way unique method. And now in a way we have perfected it, because we have done almost 5 missions like this. 3 of the lunar missions, 1 on the Mars mission, and another for the Aditya. In all of this, we made use of the same system. And then when you come very close to the other celestial object, you reduce the velocity of what you have, and then keep reaching the circular orbit that is there for the moon. So this is how we were able to get into a circular orbit of moon in the current case, or even Chandrayaan-1 case also. So now I'll touch upon when we started our activity for 2008, see, like I said, initially the prime objective of our space program was to ensure that we provide specific solutions to various problems we are facing. But at the same time, you realize that if you want to improve your capability, your capacity, unless you work on more and more challenging problems, your ability to find solutions becomes limited. So by the time Chandrayaan, that's around 2002, 2003 time frame, it was realized that you need to work on more complex celestial missions for you to achieve a greater capability even for problem solving by satellites around Earth. So Chandrayaan-1 was conceived, and when it was launched in 2008, you can visualize that man had already landed on moon by that time, and a large number of probes had touched the surface of the moon. But still, Chandrayaan-1 gets the credit for discovering the presence of water on the moon. What this really showed is that in science and technology, it is never too late. You can always do something which others have not done. What is only needed is your ability to think and ability to conceive of various missions and perform that. So what was done in Chandrayaan-1, again with the limited resources of our launch vehicle, conceiving of a satellite, which actually was also an extremely good demonstration of how you can do international collaboration. We worked with almost 5 other countries and carried some of their payloads also in the satellite. And this mission was actually very successful because it, in a way, demonstrated many things which were very different from what was believed up to that point. This slide shows you the various instruments that were sitting on that satellite. And then some of the salient results of Chandrayaan-1 was presence of water molecules in the lunar exosphere and subsurface water ice deposits. This was one other thing. And then the presence of large expanses of crystalline feldspar, then reflection of solar wind protons. Like that, actually, what this satellite did was, it also captured a large number of images, 3D images it generated. And one of the instruments that was carried on this, which was developed by NASA, also had the ability to detect presence of water and OH molecules. We also had a moon impact probe I'll touch upon subsequently, which measured the presence of even OH and water molecules as it descended from the satellite. So this showed in many ways, these are some of the images which were taken. In fact, what you see, one of the rails that is called, actually there is a region below which actually future human habitats can be there, because it's almost like a tunnel, and you can protect people or life forms from radiation effects, etc. So many of these were found using Chandrayaan-1, and a large number of papers also got published, and protons reflected from magnetic anomaly regions, etc. were picked up, and then discovery of new population of suprathermal protons around moon, and then there is also an ionosphere which was measured using the Chandrayaan-1 S-band radio occultation. In fact, what happened because of Chandrayaan-1 is, till that point, moon was considered to be bone dry. There was no water, was the general belief. But then Chandrayaan-1 changed that perspective, and then it showed not only presence of water and OH molecules, but also the processes responsible for that formation was identified. And also moon was considered to be geologically dead billions of years back. But then some of the information collected from Chandrayaan-1 showed that dynamically its volcanic activity was active, not very recent. When we talk of recent in celestial things, it is still millions of years. But then those were the change. Going back to moon happened, and you have seen subsequently large number of probes and then missions started getting formed, and in the recent past also you have seen a very significant actually increase in the interest in moon, etc. One of the things we carried on moon on the Chandrayaan-1 is what is called as a moon impact probe. In fact, it carried an object and in an uncontrolled manner, it went and hit the surface in the actually region. And this particular experiment was an inspiration from Dr. Abdul Kalam's idea that we should put the national flag on moon by carrying this. So 2008, this was done. And today, the place where this particular object landed is called as Jawahar Sthal, because there is a convention that you can demand based on what you have done certain things, and later you have also heard how the current Vikram lander's place is called Shiv Shakti, etc. Then in this particular case, it was a 29 kg object which came down, and it carried cameras, and also it carried a mass spectrometer. Mass spectrometer is an instrument which can measure a molecule in situ and tell what that molecule is, and based on that, you could identify. In fact, as it descended, it did look at OH and water molecules. But in science and technology area, if you want to prove what you have observed, you need to do a lot of validation, and it did take significant amount of time. But by that time, because of the significant data which the American systems had and previous mission, they were able to demonstrate using their M-cubed or the moon mineralogy mapper, the presence of water they could discover. And this was the first instrument, the mass spectrometer, which measured very close to the moon surface presence of water. Then the moon imaging system took large number of pictures. I'll just run through some of the images. These were all taken in 2008. As the moon impact probe started descending towards the moon, it was taking pictures, and it was also rotating, spinning. So that's why you can see the images also rotating. And it went and touched the surface very close to what is called as the Malpert region. And that was the first object we were able to put on moon. In Chandrayaan-2, obviously, what we were attempting is, of course, before this, the history was, initially we were working with Russians, where Russians were supposed to provide us the lander, and Chandrayaan-2 was supposed to carry a Russian lander. But then again, a lot of geopolitical activities, and their own program got delayed. So we decided we will build our own lander, and we built our own lander and conceived of Chandrayaan-2, and Chandrayaan-2 in 2019, it went into the moon orbit. And Chandrayaan-2, the objective was to improve on what we had done in Chandrayaan-1, and then build instruments and a lander and rover to touch down on the moon surface. While in Chandrayaan-1, some of the instruments which made impact was developed by the other space agencies in Chandrayaan-2. Every instrument that we carried were our own, and we had built newer capabilities. For example, in Chandrayaan-1, there was a microwave sensor, and in Chandrayaan-2, we had a microwave sensor which were operating in 2 wavelengths, and an infrared imager which was also operating up to 5 micron, being able to provide much more detailed data. And primary objective was, again, consolidate on what is the information on water on moon, more of lunar composition, then topography. In all these areas, we were planning to do the work with Chandrayaan-2. And of course, what happened in Chandrayaan-2 is, while the orbiter continues to function, we have collected data using the orbiter, and it is providing very valuable inputs. Our attempt to land on the surface of the moon itself, we came very close to touchdown, but then we had some problems. I'll touch upon this later when I'm talking about Chandrayaan-3's touchdown itself, what were the issues. And then we were able to collect very significant amount of data using Chandrayaan-2, very high resolution images and multispectral and hyperspectral imaging. We were able to map the presence of argon on the lunar surface. And also, like I said, we carried a 2-band microwave sensor. The microwave sensor operates in a way what is called as an active sensor. Active sensor, if you are familiar, when you take a picture using your mobile using sunlight, it is making use of the sunlight as a primary source. But when you take pictures using a flash in the mobile, it's an active sensor because you are providing illumination from your own sensor. In the microwave region, the source is always carried, and then it operates in a region beyond what we can see. Human beings can observe only between 400 to 700 nanometers, and then beyond this region, if you want to observe anything, then you have to build specific instrument which can operate in that and do. So microwave, also the advantage is it can penetrate through clouds, and it can penetrate through various certain obstructing surfaces, etc., and collect data. And another thing that happens on moon is there are certain regions on moon where sunlight never falls. They are called permanently shadowed regions. It is expected that water, if it is present, will find this region, gradually migrate it to there, and become maybe frozen ice. So if you are able to look at permanently shadowed regions, then that is where water ice, etc. is supposed to be there. And for that, using observation in very different wavelengths, you can do that. And then we also had solar X-ray monitor on that, which is a very highly sensitive instrument. And then we had this synthetic aperture radar, which is actually an improvement over what was carried in Chandrayaan-1. And using this, and we were again the first to use a dual frequency polarization-based instrument and make observation. And then how it operates is, it illuminates a certain region. Based on the scattered or reflected signal, you pick it up and then make sense out of what kind of reflection, scattering happens, and then based on that, you study the various features. You can see the kind of color images that you can create, and based on that, you can learn many things. What is the dielectric constant? What is the kind of surface roughness that is there? What kind of objects are there? All this becomes possible. And we were able to identify, again, water ice-bearing region using this fully polarimetric data. And these were all significant additions to the scientific capability of what had been happening. And this was also, again, another instrument operating in the what is called as the infrared region. This was extending the wavelength region to much beyond what was covered in Chandrayaan-1. And because of this, we are able to actually tell many more things that are happening on the moon's surface. Then actually the kind of images that are obtained, probably if you see hyperspectral means you are taking images in many very narrow wavelengths, and because of that, you can study absorptions, and then based on that, what kind of the minerals are there, you can study. So those are all the things. And in addition to that, unambiguous detection of water on the moon. And then we also carried what is called as a class instrument, which is like a fluorescence measurement. Illumination by the solar particles generates X-rays on the moon surface, and that can be picked up. Using that, you can tell what kind of materials are present, calcium, magnesium, etc., some of those things. And then you can see subsurface features can be picked up. You can look at craters, and then you can look at permanently shadowed regions. And another very important thing that was there in Chandrayaan-2, which was also one of the reasons why we were able to succeed in Chandrayaan-3, is use of this particular instrument, what is called as Orbiter High Resolution Camera, OHRC. You will be happy to know that this particular camera takes from any orbiting objects of moon the highest resolution images. In fact, we are providing this data to others now for their activity of landing, etc. Slim Japanese version also made use of this particular imaging data. You can see the kind of fine details that you can get, very small pebbles or even boulders that are there. And using this data, you can actually get a lot of details about the place where you are going to touch down. I will tell in a later slide how this ability of picking data with very high resolution helped us succeed in Chandrayaan-3. So apart from that, we also had cameras which could take 3D or 3-dimension. See, like we all have a stereo vision. Stereo vision is possible because the two eyes look at an object at slightly different angle, and our brain does the synthesis of doing parallax-based estimation of what is the distance of the object and distances and heights you can measure. So same way, if you carry 2 or more cameras looking at the same object at different angles, you can use it for creating 3-dimensional surfaces. So you can see how a crater looks like, what is the depth of the crater and elevation of that. All that is possible using this stereo imaging system. So this is also a crater known as Sarabhai crater, imaged by one of the instruments on Chandrayaan. So we also have a number of such observations. You can also do, probably you have heard, meteorites when they strike the surface of the moon, depending on the angle at which they hit the surface, it creates a crater and throws up material. And by studying the reflected signal from that, you can even tell at what angle the crater would have been formed by the meteorite, and a lot of studies are possible. Now I'll come to Chandrayaan-3 and how we were able to succeed in Chandrayaan-3, while in Chandrayaan-2 we had a problem. See, like I was telling you earlier, one of the key things was we were building our technological capability of rockets progressively. The kind of rocket engines we had built was, once a rocket engine starts, it can deliver a fixed force, fixed thrust, because that was sufficient for all our activities till geostationary orbit insertion. Because once an engine starts, the fuel available keeps on getting into the engine, and engine keeps providing the required thrust, and then you provide the velocity. But what happens when you want to land on an object in a celestial sphere? You are at a particular height, you have a certain velocity, which is called as a horizontal velocity. Now, if you bring that velocity to 0, the object, because of the gravity of the celestial object, gets pulled towards the surface. So if you don't want it to fall, like whatever stone you throw up comes down, you have to give a compensatory force in opposite direction. That means exactly the g component of the celestial object, you have to provide to the object using an engine and then compensate. So if you do that, it remains stationary there. But our task is not remaining stationary like that, but to come and touch down. That means you have to constantly vary the thrust that you are providing in such a controlled manner that the velocity of the object as it comes down and touches the surface becomes very small, in the range of 1 to 2 meters per second, or about 3 to 5 kilometers per hour. So that means the engine you are building, you should be capable of changing the thrust in a controlled manner. Like when you are on a scooter or a mobile or even a car, you press the accelerator, it goes faster. You release the accelerator, it becomes slower. So that means this is called throttling. So you have to build throttleable engines. So you have to build throttleable engines. You have to modify the engine in such a way that the fuel which is entering the engine has to change. So it was a new capability that was being built. And then any new system when you are building, you go through a large number of developmental issues, etc. So in Chandrayaan-2, what we were attempting is, we had put 5 engines on this lander, and the lander, when it was coming down and touching, all the engines had to perform in a synchronized manner. See, otherwise you can imagine the platform, if one engine is firing more, it can keep tilting back and forth. So that was one of the issues that were there. So what we did in Chandrayaan-2 was using these new capabilities, and because of certain mismatches in the behavior and also the kind of algorithms and software that was there, it was not able to handle that. So in Chandrayaan-3, what we did was, not only we modified all the capabilities, we also built a mechanism in the system such that you can test the performance of all these while you are in Moon's orbit. So while in Chandrayaan-2, not all of that could be incorporated. In Chandrayaan-3, we made sure that the engines which are operating can be verified both for their fixed thrust and also for the variable thrust by verifying their function while it is in orbit. So since all this was built into that, we could succeed. So now I'll actually showcase to you what is the real challenge and how the whole thing happens. See, one of the things you need to visualize is, if you want to go and touch down in a place, you need to know exactly what is that surface where you are touching down. So in Chandrayaan-2, we had the region based on the images up to that point. That means 2019 is when we landed. Before that, using 2008, our Chandrayaan-1 images, we had 5-meter resolution. And we were depending on some of the images from others. But then, with the kind of images we had, we could identify a region which is 500 meters by 500 meters. That was all that we had. And also, the finer details of that region was to some extent limited. But in Chandrayaan-3, what we did, using our own OHRC, we identified a region which was 4 kilometers by 2 kilometers in area. And even within that, any 150-meter diameter if you take, there is a possibility of you touching down there without your legs getting into a boulder or a crater. So now you see what has happened. From 500 meter to 2 kilometer by 4 kilometer, the margin of error between your starting point to the end point, you have a huge error margin. That means all the mechanisms which you have built of changing your speed, controlling the speed, you can allow larger error. That means you can make your programs that much more robust. So that was one thing that happened. Second thing that happened is, you will start at a point which is in the beginning, in the left-hand top, if you see, the object is moving almost at 1.6 kilometers per second speed. So your task is, starting at a particular location, at a particular instant of time, you know where you are, then progressively by measuring how much thrust you are giving and what kind of velocities are there, direction are there, you can keep calculating your position subsequently and come to the point of hovering, and there you look above that region, take a picture, map that picture or match that picture with the one you have in reference, and by comparison, you can determine how much away you have to move from where you are. So that was, starting point also, during the course of Chandrayaan-2 operations, we had built our ability to determine the orbit very accurately. So we knew the starting position more accurately. We had larger error margin in the end point. In addition to that, the amount of fuel you carry and the kind of engines that you are carrying, the engine also, if you are able to test it thoroughly, even when it is in space, you make trial engine firing and throttling. So we built all that, so you could make sure that everything is ready, and if there is any deviation in performance, we can modify our program and correct it. So that's where this particular activity in Chandrayaan 3, we were able to successfully do, because whatever problems we faced in Chandrayaan 2, we corrected it using a lot of ground tests. You will see in one of the videos subsequently, which I will show the kind of testing that had gone on ground. But even the object we carried to the moon, even while it was orbiting, we were able to verify its performance by exercising those capabilities. And in case of need, we could have corrected our programs and achieved this. So with this particular thing, the entire operation went off very smoothly. And again, many times people wonder how is it that you are able to exactly tell at 6:04 you are going to land on a So here is again one of the things you need to realize. In space, nothing is stationary. No object can remain stationary there. It's all the time moving. So that when things are moving, you need to know exactly what are the trajectories, time at which where they are going to be. So now what was the task? We wanted to land on a particular location on moon, a latitude and longitude, and there sun has to be present at a particular elevation. Because if sun is at a very low elevation, even a small object can cast a shadow, and that shadow can prevent sunlight falling on the solar panels of our lander. So if the lander touches down a place and it is in the shadow of some other crater or boulder, then you will not get power. So you cannot afford to land exactly when the sun is just above the horizon. So you have to wait for sun to come at an elevation, a certain minimum elevation. So now sun itself, if you take 14 days of sunlight available on the moon's surface, first couple of days you have to wait so that no shadow is going to cause problem. So you know at that longitude and latitude, what is the time. So the day gets fixed, date gets fixed, time gets fixed, and then all the things you have to work backwards in time and then make sure that you land at a particular place with a particular time. So that's how the time also got fixed, and then everything went as per plan, and you saw how we were able to successfully achieve this. All the instruments that were built could be verified in operation and then went ahead. And then again, the large scale, the place where we landed, like I said, you were able to actually get the images of the place, and you could get a 4 kilometer by 2 kilometer area. And then, see, you can compare the two kind of data that is there, what was available to us earlier and what we had our own, the kind of resolutions that were there. And then in Chandrayaan 3, of course, the instrument itself, how it was done. Other improvements that were done is in Chandrayaan 2, the amount of fuel we carried was limited again, because not only orbiter was there, in Chandrayaan 3, we removed the orbiter and we put extra fuel so that for any contingencies, we had more fuel available. And in fact, it was this excess fuel which allowed us to conduct the hop experiment, which was done later. And then I'm sure many of you would have seen a lot of these details. So what I'll just try to show you is a small 6-minute video showcasing what all happens behind the scene before Chandrayaan 3 mission successfully does the activity. Can you connect the audio in this? Audio is possible? Okay, can you just try? Yeah. No, it actually has an audio.
The Chandrayaan 3 spacecraft consists of a propulsion module and a lander module with a rover accommodated inside the lander. The propulsion module and the lander module are stacked together to form the integrated module. 6 modules were realized during Chandrayaan 3 project life cycle, out of which 3 were flight modules and 3 were special test modules, namely the integrated cold test, integrated hot test, and lander lift drop test modules.
The main function of propulsion module is to carry the lander module from launch vehicle injection to lander separation. propulsion module was made ready for further integration with lander module.
A six-wheeled rover is accommodated inside the lander, which would be deployed onto the lunar surface post-landing. Rover solar panel deployment and illumination test, rover standalone EMI-MC test, vibration test, thermo-vacuum test, and mass property measurements were carried out. All tests associated to rover were successfully completed, and the rover was made ready for further integration onto lander. After integration, detailed IST, sensor level alignment, and EMI-EMC tests were also carried out before shipment to ASTE Bangalore. A new facility was realized at SDSA Shah for conducting the IHT, craters and boulders simulating hazards during landing. A total of 20 tests were successfully conducted, which include 6 dry runs, 8 static tests, and 6 dynamic closed-loop tests. The lander leg drop tests were carried out to evaluate the energy absorption capability, strength and stability aspects of lander legs during touchdown. A new facility was realized at iSite with a test bed with flat and 12-degree inclined drop surface. Detailed tests were carried out at damper level, single leg level, simulator level, and fluid structure level for various touchdown velocities on flat and sloped surface and on lunar soil simulant and hard surface. A total of 15 drop tests at simulator level and 2 drop tests at fluid structure level were conducted successfully. The objective of lander is to demonstrate safe and soft landing on lunar surface. Major elements of lander include sensors, after the completion of thermal elements in the rover compartment, the rover was assembled onto the ramp using 3 pull-downs. Detailed assembly mode IST was carried out, followed by mass property measurement, thermo-vacuum test, solar panel assembly, and illumination test, EMI-EMC test at CATF iSite. This was followed by pre-dynamic deployment of secondary rover ramp, primary ramp, and rover rollout from lander, and payload deployments such as INSA and Ramba, chased, and the lander was made ready for further activities. Once the lander module was ready, it was stacked over the propulsion module to form the integrated module. EMI-EMC, vibration tests, acoustic tests were carried out. Final finishing activities such as MLI sealing, Chandrayaan-3 spacecraft was made ready for shipment to spaceport at SDSA Shah.
Okay, so that gives you an idea of what all goes behind for making sure. I'll just quickly run through some of the other sensors that were there on the lander. There was a measurement for temperature, how it changes as you go into different depths. And then there was also a instrument which is measuring the seismic activity on the surface, and then making sure that what is the variation in the electron density around the surface, and then also the laser ablation measurement. That means you fire a laser based on the evaporation that happens, measure the atoms and molecules using a spectrometer. Similarly, alpha particle instrument, etc. So then today, if you see beyond that, now we are looking at what is going to happen. ISRO JAXA Lunar program is there. And beyond that, of course, what has already been announced, that both the space station by 2035 and 2040 Indian landing on the moon. So that is the target. So now you can visualize that when India decided to put the man around Earth before the 75th anniversary of independence, even before that target is completed, you have already seen the India is setting a bigger target of landing on moon. And then what it shows is that is not an end in itself. It's only a beginning of a host of other activities. So what can be that? That means if you land on moon by 2040, what can be there beyond that? Can you use moon as a place for observatories? That means looking at from moon, both towards Earth and celestial thing, setting up observatories on moon, or moon as a habitat, create environment there where you can live, or moon as a place where you can exploit whether minerals that are there, etc. Or moon as a stepping stone for traveling beyond. Can you use it for going beyond moon to Mars or other planetary bodies, or even beyond the solar system? And then lastly, you also use it as an international collaboration thing. So this is where now India is heading for future, making sure that the next generation and all of you have an opportunity to contribute. So you can visualize that life outside planet Earth means the areas in which one has to work is so huge. Every aspect of life becomes important. And it's here there is an opportunity and there is a provision. And if you make up your mind what you want to do and how you want to do, there is no limitation, no area of work. From transportation to scientific discoveries, all areas are available. So I'll stop here, and if any of you have any questions, I'll be more than happy to take that question and answer.
Hello. Hello.
So I'll start with the...
Delete this.
Sir, I'll start with the question. If supposingly Chandrayaan-3 was not, the lander was not landed on 23rd August 2023, what would have been its next schedule?
If we have already started descent, then there is no solution possible. But before we started descent, if we had to wait and remain in the orbit for almost another lunar day. So that means one lunar cycle you have to wait, because every day you lose the duration for which you get sunlight and operate the instrument, lander and rover gets restricted. So the only possibility would have been that you have to wait for one full cycle, keep the system in orbit. We would have lost some fuel. That would have reduced our ability, and then margins available, etc., would have been the issue.
To this, it remained for 14 or 12 days. Was it experiment only for 14 days? Or?
Yeah, actually, the basic issue what you have to appreciate is on moon, on the surface wherever you are, it's almost like 14 Earth days of sunlight and 14 Earth days of darkness. When it gets into that dark phase, temperatures go very low. They go down to almost -200 to -250 degrees. So unless you have built your instrument and all the equipment that you have designed to withstand that such long durations of low temperature, then there is no way it can come back into operation. And the problem is, It's not that it's impossible to do that, but then the way to do is choose all the components such that they have verified for long exposure to low temperature, and then after that exposure they work. Then the cost of doing that would have been enormous, that is one. And the way others have done also is keep the temperatures hot by having an alternate source, like a nuclear power source, etc., heating the elements so that the temperature do not go to such low values. See, today we have components which can withstand minus 100 degree to plus 150 degree, etc., all mill standard, if you see many of them. So you have to make sure that the components and the subsystem do not go beyond the temperature for which they have been designed and validated. If you can do that, you can survive indefinitely the period.
At the thinking for future lunar missions.
Yeah, future lunar missions, definitely we have already started working with BARC also to find out how these nuclear-powered devices, what is called RTGs, radiothermal heating systems, which can provide not only heat energy, but also generating electricity from that, so that you don't have to depend purely on solar power, can be done. So these are also another areas between now and 2040 and even beyond, if you look at, you need to find ways and means by which you can generate sources. See, for example, you also saw when we penetrated up to 100 centimeters, that means 1 meter depth when you had gone, the temperature change is almost 80 to 90 degrees. Can you use this differential for generating power? So like that, there could be many things. How to find materials which can sustain. So there are huge opportunities for both research and coming up with solutions.
Thank you, sir.
Thank you, sir, for your enlightening presentation. A couple of questions from our inquisitive college students. What inspired you to pursue a career in space science?
Okay. Starting of the career in space science itself was not a, you can say in any way, very deliberate activity. But it so happened that when I was in doing physics honors in National College in 1969, man landed on the moon. We heard all that in a radio. That time, video was not there. Only through audio we could hear. So that was one of the things which was there. And it also so happened that originally I was planning to do medicine as my career. So when I completed my 12th equivalent of 12th, pre-university at that time, one of the requirements was that for joining medicine, you should have completed 16 years of age. I was born on 22nd October, so the requirement was on 1st October, I should have completed 16 years. Though I had secured the highest marks in physics, chemistry, biology from the Mysore University, getting a seat in medicine would have been assured, but because of this age limitation, I was not getting admission that year. So I decided I'll spend some time in using physics honors. So I joined National College and started doing physics honors, and then I did not look back. I continued. Then the space event happened, and later when I completed my course in Indian Institute of Science in '75, Aryabhatta had gone up in April of that year. I graduated around August. There was an opportunity to work in Ahmedabad for a program called Satellite for Earth Observation. So I had applied for that particular post. I got, and then I joined there. And I had really the privilege of working on building optical instruments for satellite applications. And in a way, you can say I have contributed. When I started my career, the first instrument we built had a resolution of 1 kilometer, and it was a 340 kilometer by 340 kilometer imager in 2 channels. By the time I completed my career, we had reached 30 centimeter resolution imaging system, not only one wavelength, hyperspectral and large number of different things. So in a way, it was, you can say, a sort of a quirk of thing that 22 days shortage of completing 16 years changed my course of life.
Amazing and truly inspiring, sir. Hope this answer is an inspiration to our young minds. The next question, what are the varied opportunities and scope available in space education for BSc undergraduate students?
See, today, unlike in the earlier era, what is available is much larger, because like I said, once you want to take life and deal with life beyond Earth, the areas in which one has to work is so wide and so large. And even when you are looking at building habitats outside Earth, whether it is an orbiting platform or on Moon or Mars, etc., the whole activity of construction, worrying about materials, surviving those conditions. So the areas in which one has to work, there is no limit. So no matter what area you want to consider, probably there'll be opportunity for you to work in future activities. So I don't think you should too much concern about which area you're picking up, but whatever area you pick up, you should definitely make sure that you understand that very well. You are capable of making a difference in that field. Not only should you know detailed about one region, but you also need to have sufficiently broad base, like it's called a T. You have a horizontal extension of many fields you are aware, but in one field, you have a deep knowledge. So if you are capable of building your capability like that, you will find acceptance in whatever you want to do. And future, like we see, is enormous. By 2040, if we want to land, and beyond that, if you have to go to interplanetary travel, from building instruments and vehicles to travel, to actually building habitats, providing living conditions from life. So it's actually enormous. I don't think you should really worry about that part. What you should really worry about, according to me, is exploring things of your own capabilities. What is it that you have, and how you can enhance your ability to deal with various aspects of life.
A great motivation. Hope our students will definitely get motivated and think of pursuing a career in space education. A question from the audience: what are the potential benefits of future lunar exploration missions for India and humanity as a whole?
Okay, so here again, probably there are a few things we need to keep in mind. If you look at Earth, because of the environment, because of the atmosphere that happens, lot of things that happen on the surface gets modified. And on the lunar surface, since there is not that kind of an atmosphere, lot of things are preserved. So by understanding Moon and learning about what is there on Moon will definitely help us understand the situation not only on Earth, what would have happened, whether it gives us a clue to making Earth more and more sustainable, survivable is one question. And then other thing is learning about Moon itself. Like I said, we can use it as a stopping point, stopover point for traveling beyond. So understanding the nearest celestial object, which is making a huge influence to life on planet Earth. It's only when you understand how the parameters which get affected on the surface, on Earth, and what are those objects which are influencing that. And I don't think you need to really put too much of effort to understand that Moon is a huge influence on life on Earth. Not only because it is producing all those tidal effects, but also producing the reflected sunlight reaching Earth and the lunar cycles that are there. So understanding what happens on Moon is definitely one of the prerequisites of being able to provide better and better sustainable life on Earth itself, apart from traveling beyond and understanding the universe.
Thank you, sir, for a resourceful answer that satisfies the requirement of the question. Any question from the audience?
Please go ahead, sir.
Mike, please.
Hello, sir.
Yeah, go ahead. Go ahead.
Yeah. Does the change in the governing body or the government of India affect the working of ISRO?
Okay. See, it is like asking, whatever you have to do, finally there are things you need to be provided resources for doing what you need to do. Who is it that can provide the resources? Obviously in India or in anything, it is the governing body. So if the governing body is able to provide whatever resources you are asking for what you want to do, you can do the job. So our problem, if you take from the past, if you see, India itself, economically, if you look at, was in a very poor condition, and it was gradually building its capability. Today, we are the 5th largest economy. So obviously, what the government can provide bodies like us is much more today than what it would have been possible few decades back. That is one aspect. Second aspect is, what also happens is, no matter who is there in the governance, when you are looking at India as an entity, what India should be doing, how India should progress, there are again certain compulsions which will come. So it is definitely those who are in the power will definitely make an impact, whether something will happen faster or slower. And they also have a lot of limitation. Though sometimes they may want to provide something, they have their own constraints. So these things play out depending on your own economic strength. Today we are the 5th largest. By the time you become 3rd and 1st, the amount of money India can spend on these programs is much more than what it is doing today. So definitely those who govern will have an impact on the activity.
Hello. I have a second question for you, and I'm satisfied with your answer. The Shiv Shakti point marks the spot where Chandrayaan 3's moon lander successfully touched down the lunar surface. There was a controversy on this topic, linking it to religion. How do you, as a working person at ISRO, take these controversies?
I think one of the key things you need to realize is in life also, there is energy is present, and energy in its various manifestation happens. And how you make use of the energy, when you say this is a point which is there, see if earlier, for example, like I said, the point where the moon impact probe touched, it was called as the Jawahar Sthal. So some name was given. So you can give whatever name you want to give. It's only a point of recognizing, and in recognizing that, it is your culture, your knowledge, and your heritage all comes into picture. So it is up to the people who are actually operating to worry about this aspect. And I will see it as recognizing that a place where something landed is being given a name which is acceptable to the people of the land and the culture and the heritage they have. Nothing wrong in that.
Thank you, sir.
So we take up the last question from respected Bhaskar Kaneparkar, sir. Please hand over the mic.
Here. Give here.
Sir, not a questions, I have 2-3 doubts. See, whatever knowledge that we gather about space is from the newspapers and the electronic media, as we are not the students of physics, astronomy. So one was, what is this cryogenic engine, and why was it so essential? And why we were denied that technology? That was one. Second was...
Shall I complete the answer for that? Okay, first. See, one of the thing is, whatever rockets you are building, that rocket, when you have to carry objects and all that, its ability to generate the force and how much minimum mass it is using in doing that, and how long it can provide that force is important. See, if cryogenic engine, the advantage is both liquid hydrogen and liquid oxygen, which are the two essential components, which when they come together, they produce the required force. So you are storing the material in the liquid form, and you are calling it cryogenic because the temperatures are very low. Now the cryogenic engine, what it does is, the liquid hydrogen and liquid oxygen which is stored, after that it is converted into gaseous form, and in gaseous form it is brought to a place, the engine, and where they come together, they generate, because of the combustion, generate the thrust. So now the cryogenic engine is important because it is with smaller mass you are able to generate larger force, and higher forces you are able to generate is what is required for you to carry heavier mass into space. And for that mass, unless you provide a required velocity, it will not do the task of going around Earth or going to another point. So the basic idea, the cryogenic requirement is being able to use less lesser mass for generating the required forces. That was the thing. Of course, the challenge is storing them at the required temperature, because otherwise quickly heat in leak will make it evaporate and go away. So you have to keep it, refrigeration system should be such that it is kept at very low temperatures. And then you can imagine the engine which is actually firing, even for 1 second, if it is not cooled sufficiently, engine will melt. So the technology is very involved. So because of that, it was difficult. While one superpower was ready to give, another superpower ensured that it did not happen. And why is, again, it's a human nature. Once you have achieved certain capability, you don't want everybody else to achieve that because your dominance goes away. That is one. The second thing is, when you come very close to doing it, they are ready to give you that technology because they don't want you to go further in that. Anyway, that is aside. The basic answer to your question is, cryogenic technology is basically making use of lower mass material and providing higher ability to provide forces. Okay.
Thank you, sir.
The next is whether we are following this elliptical path to go to the
elliptical path.
Yeah, because our engine capability
is less. Correct.
Does US also follow the same method, or do they go directly?
No. You saw, for example, just few days back, one of my Elon Musk rocket took straight in 5 days they reached the moon, whereas we took almost 20 days, etc. So depending on the rocket capacity to provide, you can do in a shorter period. And they have much heavier engines, much more capable engines. We have not yet built such capability. That's where the resources, what she was asking, how much resource is there. If given the resource, you can build higher capacity. So currently what we had is a limited capacity. So we augmented it using our satellites.
And then lastly, if we can have such cryogenic engines of such a technical scale, why we are not able to build engine for Tejas?
Give?
Why we can not build engine for our Tejas aircraft?
Okay.
When we are building such a fine engine to send tons to moon, why we can't? Why we have to import Rolls-Royce?
Yeah, I agree. So this is where, again, another thing what you have to see is different domains have so many different aspects of life that comes into picture. If you are to really look at it in a sense, when we got independence, aeronautical industry in India actually had a lot of capacity. Somehow that was not nurtured. And if it had been nurtured, probably today it would have been a different thing. But a lot of things happen because of people who are actually running the systems have their own priorities, and what they think is right or wrong determines the course of the various things. So whereas in space, you are able to do it because you are not actually bound by the constraints of land. You are doing everything outside. And there was not too many heritage things. There were very few people who were working in that area at that time. Whereas aeronautics had too much of dominance of others.
That concludes our question and answer session. Let's give a big round of applause to Shri Kirankumar ji for enlightening responses, and to all our audience members for their thoughtful questions. Requesting Honorable Secretary, Principal and Vice Principal, Ponda Education Society, to occupy the seats on the dais. Atiti Devo Bhava. Today, as we embrace this noble sentiment, we are privileged to honor our esteemed chief guest with a token of appreciation. On behalf of our institution, Ponda Education Society, I take this privilege to invite Honorable Secretary Shri Ritesh Naik to present a memento to the distinguished speaker for today's program. On behalf of Goa University, may I now request our principal to present a memento to the guest speaker. This memento symbolizes our profound gratitude, love, and respect for your unwavering commitment towards the event. Thank you, sir. As we conclude our discussion on India's remarkable journey into lunar exploration, let us remember that the sky is not the limit, but rather the beginning of endless possibilities. Ladies and gentlemen, as we draw near to the conclusion of our event, it's time to express our gratitude to all those who have contributed to its success. Adding significance to this moment, let me invite Dr. Rasika to propose a vote of thanks.
Thank you, Dr. Meeta. Respected resource person, honorable guests, all the dignitaries on the days, of the days, beloved students, ladies and gentlemen present here, wish you a very good evening. I, Dr. Rasika Desai Gaukar, am privileged to propose the vote of thanks on behalf of PES's Ravi S. Naik College of Arts and Science, Farmagudi, Ponda, Goa, the organizing committee of today's session. We are all happy and grateful for this successful program. I extend my heartfelt gratitude to each and every one of you for gracing us with your presence at this enlightening public lecture on Indian lunar missions by Shri A.S. Kirankumar, Chairman of the Apex Science Board and former Chairman of ISRO. We are truly privileged to have had the opportunity to delve into the intricacies of India's lunar exploration journey under the expert guidance of Shri Kirankumar. His wealth of knowledge and insightful perspectives have undoubtedly enriched our understanding of the remarkable achievements and challenges in space. Special thank you to Shri A.S. Kirankumar for sharing his valuable time and expertise with us. Your illuminating discourse has left an indelible mark on our understanding of India's contribution to the lunar explosion. I express my gratitude to the Chairman of Ponda Education Society, ex-Chief Minister of Goa, present Minister for Agriculture, Civil Supplies and Handicrafts, Government of Goa, Shri Ravi S. Naik sir, who could not be present here today due to unavoidable circumstances. Sincere gratitude to the Secretary of Ponda Education Society and the dynamic chairperson of Ponda Municipal Council, Shri Ritesh Naik sir, for gracing this occasion. I also express my gratitude to the principal of PES's Ravi S. Naik College of Arts and Science, Professor V.J. Pisullekar, sir, who has been the main pillar behind organization of this event. Sincere gratitude to our Vice Principal, Dr. Satish Keruskar, sir, for organization of this event. I express my gratitude to the entire organizing committee, volunteers, faculty members, and the administrative staff, and everyone who was involved in making this event a resounding success. Your hard work and dedication have contributed to the success of this intellectually stimulating evening. I must mention our deep sense of appreciation to the entire team of Rajiv Kala Mandir for providing us this prestigious Kala Mandir located in the beautiful city, the Antruz Mahal, Ponda. We are grateful to the Treasurer, Ponda Education Society, Shri Prakash Barve sir, GVM's Management and Governing Council authorities, Shri Bhaskar Khandeparkar sir, Shri Krishna Shetye, Shri Jayant Mandurkar sir for gracing this occasion. We are also grateful to the Goa University, ISRO, Directorate of Higher Education, Government of Goa for the organization of this session. I would express our deep sense of gratitude to all the distinguished guests, special invitees, principals of various institutions, members of the press, faculty members and administrative staff, and beloved students from various institutions from in and around Ponda who are present here today. We would like to express our gratitude to Mr. Vishnu Naik for the invocation song and Dr. Meeta Amonkar, Head Department of IT and IQAC Coordinator, PSS RSN College, for comparing the entire session. To our esteemed audience, thank you all for your active participation and engaging discussions. Your enthusiasm contributes significantly to the vibrant atmosphere of learning and sharing ideas. We would like to thank all the known and unknown hands that contributed for the success of this program. Let's carry forward the inspiration gained from this lecture as we continue to explore the vast realms of science and technology. Thank you once again, and we look forward to more such enlightening sessions in the future. Jai Hind. We will now stand for the